Okay. So now we will first just take an example of this tetrahedral because I introduced the cubic uh, point groups. The tetrahedral is one such example. So we will understand what is this tetrahedral symmetry and how do we find out which is symmetry element is present over here. So it's very simple. You need to see uh, we are having these tetrahedral in this tetrahedral we are having this we are having these elements. E identity is for sure there in every molecule. Now we need to find out how it is having 8 C3s. So basically, what is C3? C3, if you will see this molecule, this is a tetrahedral one. And if I am talking about C, H1, H2, H3, and H4, I'm taking an example of CH4 methane molecule. Okay, now we have seen this is not a linear molecule. Okay, this is not a linear. We find out whether it is a cubic. Yes, it is a cubic. Now we need to find out how many elements and whether it actually comes in the category of tetrahedral symmetry or not. So what we will do, we need to find out which SC axis is there. So firstly, if I will try to have a C4, C4 will give a rotation of 90 degrees and 90 degrees will not give me an equivalent conformation. You please try on your own. If my this H3 is back of the plane and this is front and these two are in plane, after giving 90 degrees rotation, this would go out of the plane and these would come in plane and that would not give you an equivalent conformation. But what about C3? If I have one C3 which is passing through, if I have C3 which is passing through one C bond, you will see that all the other three hydrogens would be rotated by 120 degree, giving you an equivalent conformation. So since we are having four vertices, we have four vertices in tetrahedron. So therefore, there would be four C3s and each C3 would be going from along the one vertex, that is C and H bond. So this one vertex is this hydrogen and it is passing through, C3 is passing through this one, uh, giving a rotation to other three hydrogens. And we know that each C3 gives an operation of C31 and C32. So therefore, if one C3 is giving you two C3 operations, therefore 4 would give you 8 operations. So that's why there are 8 C3s. So this is clear? Okay. Now moving ahead, we need to find out whether there is any other axis present to it or not. So we found that besides the C3, we have C2s also. How the C2s are there? So if we have this is an edge comprising of this one, and this is an edge. So these edges, if we are passing, if we are passing the axis opposite in between the two opposite edge centers, that would form your C2, and there would be three C2s present because we total have 6 edges, and we are talking about a C2 is passing through the two opposite edge centers. So therefore, there would be 3 C2s and each C2 gives one operation. Therefore, we will be having 3 number of symmetry operations. Along with C2, we will be having S4 also. And we know that one S4 gives you an operation, symmetry operation of S41 and S43, which is 2. Therefore, there are 6 S4s. And when we have C2s, in between two C2s, bisecting the two C2s, we would be having a sigma D. So they bisect two C2s. So that is called a sigma D. Since we are having three C2s, so we will be having for each C2s, there would be a bisecting plane. So in between the two C2s, we'll be having, and there could be a lot of combinations. So therefore, we'll be having 6 sigma Ds. And similarly, one identity is of course there. So if you calculate that, that would give you 24 symmetry elements. So this was about today's concepts, like what we have seen in week 1 and week 2, about chirality, about finding the point group, how different numbers are there, how would you go to call some molecule as a single axis point group or dihedral or a cubic, and then how to identify it through this particular chart, how to call some molecule as a chiral molecule. You need to find out whether there is any SN axis present or not, and also whether they belong to CN or DN chiral point groups or not, and what are the different enantiomers possible for this chiral molecule that we have understood, and besides we have understood the tetrahedral molecule. Now these are the assignment problems for week 2. We'll first look into the assignment problems of week 1 which have been left out. So I hope you have tried it by yourself. Now we'll quickly see this question number 2, where it has been asked that predict the equivalent structure on applying the following operations on platinum Cl4. So you need to know what is the structure of platinum PtCl4. So we know that PtCl4 forms a square planar structure. So I am just drawing Cl, so giving you a notation because we are going to apply some operations. So this would be useful for us. So firstly, we have to apply C4. So C4 rotation I am giving. Since I'm talking about this is a planar molecule and this C4 will pass through the platinum. So I am calling this as the Z-axis. Now when C4 passes through Z platinum along the Z-axis, C4 is nothing but a 90 degrees rotation. And if we are saying it's a square, and we know all the squares are having an angle of 90 degrees. So this Cl will ultimately go to next position, and this would be your equivalent conformation. So this is done. Now, what happens if you're giving a sigma H to this one? Now, this molecule is already in a planar molecule, which is your sigma xy, because your axis, principal axis, is your z direction. So this is perpendicular to your C4Z. When you're giving this one, it would maintain its structure as it would only bisect the molecule. It will not reflect anything as the molecule itself is a planar molecule. Now, this is also done. We got the equivalent conformation. Now, what you have to do, you have to apply this C4 into sigma h, and we have already read that we have to do right side first and then the left side. So first apply the sigma h, which we have already done, which is giving me an equivalent conformation. And after that, I'm going to apply the C4C, which is giving me this conformation. So ultimately, this is my product of C. So we did the similar way. Firstly, we bifurcated it, and then we have a sigma 4 into sigma h, and we ultimately got the what we have given for the C4 itself. So this was pretty straightforward. Now there is a question says that if we have an S2 operation on a molecule with axis of rotation, so it says that we have to apply an S2 operation on a molecule with axis of rotation on Z-axis, move the nucleus XYZ. So we know that S2 we are talking about. S2 is what? S2 is C2 into sigma. And now when we are talking about C2 into sigma, it has already been defined that this is the Z-axis. So this would be your C2V, and perpendicular to that it is sigma XY, right? So now you have to apply this particular conformation operation on XYZ nucleus. So individually, we will do it X, Y, and Z. You can solve it mathematically also, X, Y, and Z. Now, when you apply an operation of C2Z on XYZ, what you will be having? So what you have to do, firstly, you have to apply the right side operation, which is sigma XY. So this would remain as it is. So first we apply So first we are going to apply sigma xy. So sigma xy on xyz is not going to change anything about x and y because that is the plane containing axis. So only the z would get reflected to minus z and we would end up having xy minus z after the application of after applying sigma xy on xyz coordinates. So we get z goes to minus z. Now, when you're saying that you have to apply C2 on this one, but C2 is passing through z direction, so it is not going to change. Only the x and y would be uh, rotated by 180 degrees. And we know that x rotation by 180 degrees minus x, y rotation by 180 degrees minus y, and minus z would remain as it is because C2 is along the z direction, right? So this is what we got, that if we are applying S2 on x, y, z, it would give you minus x minus y minus z. If you will carefully see, this is nothing but the inversion center. That is right. So actually S2 is nothing but your I. So when you apply anything on any coordinates, you will end up having minus x minus y minus z because it actually goes to 180 degree onto the opposite end. So this question is done where we get the answer as D. Moving ahead, we need to find out the order of the following molecules. So firstly, point group we have told order is nothing but the total number of symmetry elements which are present. So order of the molecule is the total number of symmetry operations present. Say for example, H2O, we have already seen H2O is having a point group of C2V, which is E, C2Z, sigma xz, sigma yz. Total number is 4. HCl belongs to your linear molecule since they are different and they are having a C infinity. So therefore, this is C infinity V. This would be having infinite number of, this is the order is infinite because there are infinite elements. When we have a H2O, H2O2, cis molecule, so it is having a C2 and it is also having, it is similar to that of water molecule. So it is also C2V with a number order of 4. And trans H2O, if you will draw, it is having C2, but it is not having any sigma. So there is identity C2Z and there is sigma XV, which is a molecular plane uh, bisecting your molecule in two halves. And also, if you will carefully see, there is an inversion center because from the center to the opposite end, we are getting the equivalent structure. So the order is again 4. So this is the way you will calculate the order of your molecules. Now moving ahead, we have another question, which is how will you differentiate between a facial and the meridional isomers of ML3X3 based on the symmetry elements? So firstly, we will understand what are meridional and facial isomer. If your L is one type of ligand and X is another type of ligand. And if you're having all the L in one directions, this kind of scenario is your facial isomer. And if after 2, there is in between an X, that is a meridional isomer. Now here, if you will carefully see, since it does not belong to an octahedral cubic symmetry as there are two different ligands, so we need to find out what is the principal axis over here. So if you will carefully see, these three axes form one triangle and these three L, they have one triangle. And if I am having a C3 from the center, so C3 goes from here. So by all the, if there is a 120 degrees rotation, then all the X would be rotated by 120 and L would be rotated by 120, and therefore C3 would be present as it will give you equivalent conformation. So corresponding to that, this is C3. Similarly, C3 is there, but we don't find any C2s over here. There is no C2 present over here, because even if we take any axis, it would not give anything. But corresponding to C3, there would be 3 sigma V's. And so this belongs to C3V point group. Now, if you will see here, we have so here there is no C3, but if I am having a C2 in this direction, then my X and X are reflected and L and L are there. So C2 is there. Corresponding to that, we have 2 sigma V's as well and E also. So therefore, this belongs to C2V. So facial isomer gives you C3V point group, whereas meridional gives you C2V. Therefore, we can easily identify based on the number of symmetry elements present over here. So this you have to try by your own. H2O2 open book, what is the order? Number of improper rotational axes in case of S4, please try and solve it. We have already discussed for the case of S6. And define how many C3 operations are there in octahedral and tetrahedral. That is for your homework. Now moving towards the week 2 assignment problem. So as we have already talked about the point group today and the number of symmetry elements, the first question says, what is the total number of symmetry elements present in the eclipsed sphericene, or I would say the order. So firstly, you should know what is the eclipsed sphericene. So eclipsed ferrocene is nothing when the angle between the two CP rings is 0 degree. So if I have iron here, so one CP ring cyclopentadienyl is facing this direction, other also goes and face this direction. In this one, if we have a C5 axis of rotation, if you'll do, then the hydrogens of both the CP rings would be rotated by 72 degrees, and therefore we'll get an equivalent conformation. Corresponding to that, there are also 5 C2s perpendicular to your C5. And since it is also having sigma h, we don't need to find any further anything. So this would correspond to D5H. And D5H is having a total number of 20 operations. So you can just count for this one and try to find out by yourself, because it would be having S5 also existing. So what are the number of S5s present over here? You just try to find out. So you should know the structure of your molecule, and if you know what are the main things that you need to find out, you will be ended up having a D5H. And a trick to find out the number of operations, just in a quick response, if you have a D5H, so you just multiply the 5 number with 4, you will get 2 answer. Similarly, if you have C and V, then you need to multiply with 2n. Say for example, C2V would give you 4 order, C3V is 6, D6H would be your 24 operations, and so on and so forth. So it's a general trick. When you solve a lot of problems, you will ultimately get to know about it. Moving ahead, so here's the question which says that if you consider a non-linear molecule with E, we have given E, C2, two C2s which are perpendicular to the first C2. We have sigma D, we have sigma S4. So we easily say that when we have a C2 and when we have Cn and we have NC2s perpendicular to Cn, that does not come in these two categories, because this is a single axis rotation group. And these are the dihedrals which requires this NC2 perpendicular to Cn. Now the point of thing is, here we are talking about sigma D, and D2H does not have sigma D. only D2D is having. So the answer was clear. You don't need to mug it up. You just find out how you can eliminate the other two options to come to the proper answer. Now, which of the following groups belong to the cubic groups? It's very simple. It's tetrahedral and octahedral. C4V belongs to your single axis group. And this belongs to your dihedral group. Now, the next statement is find out the correct statements about chirality. So it should be superimposable mirror images. No, it should be non-superimposable mirror images. And centrosymmetry, they shouldn't be having any I or sigma. The point groups Cn and Dn belong to the chiral. Now find out whether the H2O2 open book is chiral or not. So we have the structure of open book. Or you can consider the laptop also. So here your one side you will be having one OH and other side is one OH. If you will see, this is only having C2 point group. No other element is present and that is chiral. But since this OO bond, if it will give you a mirror image, so this would form as this way. But due to the single bond or rotation, it would again form this. So due to the single OO single bond rotation, chirality is lost. So even if it does, so it is not chiral. It's very important question. You need to understand, even though it belongs to CN point group, which is chiral, but due to the inherent property of single bond rotation, it loses its chirality. Therefore, H2O2 open book is not chiral anymore. So here you have chromium ethylene diamine complex. We need to find out whether it is chiral or not. If yes, then find out its enantiomer. So I'm solving it over here. So ethylene diamine, we have ethylene diamine, that En is nothing but your two NH2 groups bound with CH2. So this we are defining as NN. So here I'm N, N. Okay. So now this is your chromium En thrice 2 positive charge is outside. Now you need to find out whether it's chiral or not. Find out the point group first. It's cubic. No, it's linear. No. Now what is the principal axis present over here? We can easily see that this forms the, so this forms a triangle over here. And here it's an inverted triangle. Therefore, C3 is there for sure. Also, since all the atoms are similar, they also comprises of three C2s. Therefore, there is a D3. So D3 point group is chiral in nature. So this is chiral molecule. And corresponding to that, it would be having lambda and delta isomers, which you can easily draw. If you will check this one. So this is your, what I have made. This is front to back. It's the anti-clock. So therefore, this is lambda isomer. You can easily form the delta also. This was the answer for the question 7. Now, number of C2 axes present in the CCl4. You know that CCl4 also belongs to a tetrahedral kind of symmetry. Now, we know that how the C2s are present. C2s are present uh, passing through the opposite edge centers. And we have six edges, therefore three C2s are there. The answer is three because it would be passing by two edge centers at one time. So with this, our assignment problems for this particular week is done. And whatever the extra questions that I have given, please read about it and try to solve by yourself. So what we have done for today is we have first we have taken up the questions from the last week. If you have a PT-cell4 molecule, you can apply the C4Z as well as sigma H and find out which equivalent conformation you'll be having. Similarly, then when you apply a S2 operation into any coordinates, you will ended up having an inverted coordinates. Therefore, S2 is equals to inversion center. Then we found out the order, that is the total number of symmetry operations present in one molecule. So for all the molecules, you can try by yourself by using different molecules as well. Followed by with the help of the point group and number of symmetry elements, we could easily differentiate between facial and meridional because facial isomer follows C3V point group and meridional is having C2V. This you have to try out, which we have already seen that H2O2 is open book. So the symmetry elements we are seeing is C2 only and the order is 2. It is having E and C2. This is chiral, but H2O2 is not chiral. So you need to remember this fact for sure. And reason also because of the single bond rotation. Number of improper or rotational axis operation in S4 case. So in S4 case, if you will just see, we know that we have to try till it does not give us identity. So it is C41 and sigma 1. So C41, sigma 1, it is countable. S42 is C42 into sigma 2. C42 is nothing but your C2 and sigma 2 is identity. So this is your C2 rotation. So this is not counted. S43, C43 and sigma 3, which is C43 and sigma. This is counted. Now we have S44, C44 into sigma 4. C44 is identity. Sigma 4 is identity. So therefore this is identity. It is also not counted. So S4 gives you only S41, S43 improper axis of rotation, rotation axis operations. So this is also done. This is also done. So we are only having two. Now define how many C3 operations are there in the octahedral and tetrahedral. In tetrahedral, I've already told you the tetrahedral point group. Tetrahedral is having four vertices and therefore it would be having four C3s and one C3 gives you two operations. So therefore four C3 would give you 8 operations. So the answer for this one is 8. In octahedral also, you need to find out the different elements which are present for octahedral. We have already discussed this earlier that we have in octahedral we have 6 vertices, 12 edges and 8 faces, and C3 goes through between opposite faces. So if you'll just see that, you will get to know. And we have 8 faces, so therefore there would be 4 C3s, and each C3 gives you 2. So therefore 8 C3 operations for octahedral as well as 8 C3 operations for tetrahedral. So this you can just try and find out by yourself to be on a safer side. So this also we have discussed in the class itself. So you just try and figure out Moving ahead, this was a repetition and discussion about the previous lecture. Combinations we have discussed today about the non-rotational groups, which belongs to C1, CS, and CI. If it is not having any improper axis of rotation and only having identity, or the plane of reflection, or the invergent center, then the separate groups are called as non-rotational. Then when we are having a single axis rotation group that is only having Cn, Cnv, Cnh, S2n, and C infinity V. Similarly, the dihedral group starts with D, which is bound to have n C2s perpendicular to your principal axis Cn, and the cubic groups tetrahedral and octahedral, which are having the more number of elements. So that is a different classification. Then followed by, if you need to find out how to find out a point group of a molecule and what is a point group. So it has been made to make our job even more easier. So for two different molecules, they can be a similar point group. So point groups is defined only based on the number of elements that are present in your molecule. So it's a mathematical group which would involve all the symmetry operations that can be performed on a molecule, resulting into a conformation which would give you an indistinguishable conformation from the original one. So for example, we saw the H2O or H2O, which we denoted as HA and HB on C2 rotation along the Z direction, we got HP, HA changing their positions, but that is an equivalent conformation. Therefore, it does count in the calculation of a point group. So now, so how to find out a point group of a molecule? It's quite straightforward. You need to follow this particular trend. If it is linear, then go to the linear point groups. If it is non-linear, then first check whether it's cubic. If it is not a cubic, then you need to find out whether the Cn axis is there or not, which is greater than 1, that is C2 or more than C2s. If it is yes, then you find out whether there is any other C2 present. If one C2 you find out, that means other C2s would also be there. Moving ahead, you need to find out whether sigma H is there. If yes, then it is CDNH. If not, then find out whether sigma D is there. If yes, then DND. If no, not present, then DN. That is dihedral groups. If at this point, if you don't see any CN, then find out whether sigma is there or not besides the identity. That if yes, then it is CS. If not, then find out whether I is there. If invergent center is there, is CI. If not, then it is C1. At the same point, if after CN identification, if you don't find any C2 perpendiculars, then you need to find out whether there is a molecular plane or not. If yes, then it is CNH. If not, then it is sigma. Then find out whether vertical plane is there or not. If yes, then it is CNV. If not, then it is CF. So this way you can find out the point groups very easily in any molecule. And after that, we talked about the chirality, that how we get the non-superimposable, indistinguishable mirror images. And what are the point groups? What is the criteria of being a chiral? It shouldn't be having any SN axis, that is improper axis of rotation, which involves both plane of reflection as well as the invergent center, followed by the point groups for chiral molecules. CN and DN are the 2 point groups which follow this trend, but you need to be very careful if there is any flexionality behavior and if chirality is lost by single bond rotation or not. So you need to be careful. And what are the two isomers? We have delta and lambda isomers. If your movement from front bond to the back atom goes to left side direction, that is the lambda. And if goes from right, that is your delta. And based on that, we have discussed all the assignment problems for week 2 as well as. So hope this is clear for all of you. And if there is any question, you can post your question in the chat box or unmute yourself. I'll be happy to answer your questions. So this material will be available to you guys, as well as the lecture would be available on YouTube. You can go back at any point to check it out. Thank you.